This is the start of chapter 2, where we discuss strain. The first chapter had 8 sessions. This is session 9. Here we introduce strain and discuss the stress-strain curve. This is the roadmap, and we can see where we are in the overall scheme of things. We are starting chapter 2, and we are in session 9 as shown. We now introduce strain. At the start of the second section of the first chapter, we mentioned that there were 2 different classifications that can be attributed to mechanics of materials as a whole. Thus, mechanics of materials can be considered to be a study of strength, deformation, or stability. The first chapter was related to strength, while this second chapter is more devoted to deformation. The second classification mentioned that mechanics of materials either involved Newtonian mechanics or experimental study. The first chapter involved Newtonian mechanics, and this second chapter will involve more experimental study. Consider a bar subjected to a relatively small load P as shown. The bar extends by del L. The extension del L is due to the load P. We consider that equal portions of the bar contributes equally to the total extension. So consider that this bar is divided into 3 equal portions, L by 3 each. Then any of the portions will extend by del L divided by 3. So unit length of the bar will contribute to del L divided by L in the total extension. The extension due to unit length of the bar is referred to as normal strain. For tensile loading, the strain is considered positive, while for compressive loading, the strain is considered negative. So here the strain is positive. Axial loads, as the case here, causes normal stress and normal strain. In the case of shear loads, the stress would be shear stress and the strain would be shear strain. Now in this case, where a load P is applied to a bar of length L and the extension is del L, then it is experimentally found that del L depends upon the length L, the force P, and the cross-section area of the bar, that is a perpendicular cross-section. Thus, del L is proportional to PL divided by A, or del L divided by L is proportional to P divided by A. Now del L divided by L is the normal strain, and P divided by A for this case is the normal stress. So strain is proportional to stress. In the second section, of the last chapter, we discussed stress. In the last slide, we discussed strain. So, if a load P is applied to a bar as shown, perpendicular section will be subjected to normal stress. If del L is the extension in length of the bar, then del L divided by L is the strain. In the last slide, we discussed strain when the load was not high. We mentioned that stress will be proportional to strain. So for loads that are not too high, the stress versus strain curve is linear. However, if we keep on increasing the load P, then at a certain stage, the curve will become nonlinear. We can keep on increasing the load till the component fails. Such a curve of stress versus strain is called a stress-strain curve. A stress-strain curve can be developed for tensile loading, as is the case here, but it can also be developed for compressive loading. With tensile loading, as the length extends, there's also a reduction in the cross-section area of the bar. We'll discuss such reduction in the cross-section area later on. We have already mentioned that normal stress is proportional to normal strain, but we'll discuss more on this aspect. We'll also discuss the relationship between shear stress and shear strain. Now we look at stress-strain curves. We specifically discuss tests carried out to determine these curves and different types of stress-strain curves. Stress-strain curves are obtained based on tensile tests. This is a tensile test specimen. So loads are applied at both ends and gradually increased till the component fails. The stress and strain value in the component is determined throughout the process. They are then plotted in a stress-strain curve. Before application of the load, this length, load known as the gauge length, is marked off. The initial cross-sectional area is also recorded. The gauge length is referred to as L0 and the initial cross-sectional area as A0. We have already discussed the fact that with increase in tensile loads, even at low loads, the cross-sectional area reduces. At higher loads, as we enter the nonlinear portion, the reduction in the cross-sectional area is more pronounced. To start with, we differentiate stress-strain curves into two types: engineering stress-strain curves and true stress-strain curves. In engineering stress-strain curves, the reduction in the cross-sectional area is not taken into account, and calculations are done based on the initial cross-sectional area. So stress is found using A0. Similarly, strain is found using L0. So stress and strain are found using these expressions. Strain is increase in length divided by the original length. In the true stress-strain curve, the actual cross-sectional area is used. Also, to find strain, the changing length rather than the initial length L0 is used. Stress-strain curves can be obtained for compression as well, as earlier mentioned. Stress-strain curves for high temperature and high loading rate can be quite different and will not be discussed here. Stress-strain curves of brittle and ductile material are different. We earlier differentiated between the engineering stress-strain curve and the true stress-strain curve. Most of our discussion will involve the engineering stress-strain curve. As earlier mentioned, this stress-strain curve is different for ductile and brittle materials. Within ductile materials, we'll discuss two different types of engineering stress-strain curve. The first curve relates to structural steel. So this is the stress-strain curve of structural steel. It is given by A, B, C, D, E, F. For the initial portion AB, stress is proportional to strain. B is called the proportional limit since the proportional behavior ends here. Stress in this region can be given as strain multiplied by the slope of this linear portion. The slope of this linear portion is referred to as E and mentioned in literature as modulus of elasticity. Modulus of elasticity is a material property. Between B and C, we see that there's a larger increase in strain for an equal increase in stress. C is called the yield point and the corresponding stress is called the yield stress. For a material loaded up to C, if the load is removed, then the material will regain its original dimensions. The behavior in this region is called elastic. For a material loaded beyond C, it will not regain its original dimensions when the load is removed. This region is called the plastic region, and after removal of load, some plastic strain will stay in the material. Between C and D, there's an increase in strain with little increase in stress. The behavior is called perfectly plastic. This region is often much larger than shown in this schematic diagram. Between D and E, the material undergoes strain hardening. The structure of the material rearranges and higher loads are required for further strain. Again, this region is much larger compared to the strain at E. We earlier mentioned that there's a reduction in the lateral cross-section as loads are increased. This reduction is quite pronounced in the plastic stage. However, after the ultimate stress is reached, a specific localized area undergoes reduction in cross-section. This phenomena is called necking. After that, for further strain, less stress is required. The neck portion keeps on reducing in cross-section area till the component fails. We initially mentioned that there were two different types of stress-strain curve for ductile material. Earlier, we looked at the stress-strain curve of structural steel. Here, we look at the stress-strain curve of aluminum, which is the second type. So this is the schematic diagram of the stress-strain curve for aluminum. As we can see, this is quite different from the stress-strain curve of structural steel earlier discussed. The initial part of the curve is linear and there's a proportional limit in the curve. However, there's no distinct yield point. There's a large increase in strain with a fair increase in stress as well, as we can see from this portion. Since there's no distinct yield point, we artificially find an yield point in this curve. In order to find the yield point, we take a 0.2% strain offset as shown here. The strain offset is drawn so that it has the same slope as the initial portion of the stress-strain curve. This initial portion is linear. Wherever this strain offset line cuts the stress-strain curve, we refer to that point as offset yield stress. We now look at ductility. There are two different ways of giving ductility. One using length and the other using area. The one using length is given as the increase in length by the original length into 100. So the measure is given as a percentage. Now consider A0 as the original cross-section and A as the cross-section at fracture. Then ductility using area is given as A0 minus A divided by A0 into 100. So again, the ductility here is given as a percentage. We now discuss the stress-strain curve of brittle material. As we can see, the plot here is slightly curved. The elongation after proportion limit has been reached in brittle material is minimal. In material such as glass, this line is a straight line. In brittle material, ultimate and fracture stress is the same. This is different from ductile material. The change in cross-sectional area at failure is minimal for a brittle material. Also, the strain is small at failure. We discuss here compression stress-strain curves. We earlier discussed about the specimens used in tensile tests. For compression, the specimens used are small cubes or cylinders. Both for ductile material as well as brittle material, the initial part of the compression stress-strain curve is linear. For structural steel, the yield point in tension and compression are the same. Here it can be seen that in a ductile material, the resistance of the material increases. So this is very different from a tensile stress-strain curve. The increase in strain becomes lesser with the increase in stress. For brittle material, the failure strength in compression is higher than the failure strength in tension. However, material do fail in compression. We next look at two stress-strain curves. Earlier we discussed that with two stress-strain curves, the stress is given by the load divided by the actual area rather than the initial area A0. So as load increases, the area becomes smaller and the stress is higher than the engineering stress. As shown in these diagrams, the stress keeps on increasing, unlike the engineering stress-strain curve. When necking occurs, there's a reduction in area and as such a corresponding increase in the stress. In the true stress-strain curve, not only the variation of area is allowed for, the variation of strain is also allowed for. While in engineering stress-strain curve, only the initial and the final length is used to find strain. With true stress-strain curve, as the length varies from L0 to the final value L, the increase in length compared to the length at all intermediate stage is used to find strain. The del epsilon is given as del L dash by L dash, where L dash is the length at any stage. The strain when the length L is reached is given as epsilon true is integration of dl dash by L dash from L0 to L, which becomes ln L by L0. While the engineering stress-strain curve is different for compression and tension, the true stress-strain curve remains the same. Earlier we dealt with stress-strain curves related to loading only. Here we deal with stress-strain curves related to unloading and reloading. Consider an element subjected to uniaxial loads that keeps on increasing. So the stress-strain point will start from O, it will move through I to K, A and C. Here we have only loaded the element. I is the proportional limit and K is the yield point. Now we can see that the stress strain point A has some plastic strain since it is past the yield point. Let us consider the case where the element is unloaded at A. It will then pass through A, B. It will lose its elastic strain but still have the plastic strain which is given as OP. If we reload the element, then it will pass from B to A to C. A is its new yield point and its yield stress is higher than the previous yield stress. Now we consider another element which as earlier is uniaxially loaded and the stress strain point pass from O to D to E. D is the yield point, so at E it has some plastic strain. If we unload it, it will follow EF. So it will lose its elastic strain but retain its plastic strain which is OF. After unloading, consider the case that we will apply uniaxial compression load. In that case, it will follow FG. At G, it will yield under compression. Now, a component without any previous loading under tensile load yielded at D. And if the same component is subjected to compressive load without any previous loading, then it will yield at D dash. The yield stress at tension is equal to the yield stress in compression. Experiments show that Fg is smaller than OD dash or OD, which means that a previously loaded component will yield at a lesser stress under compression compared to a component that hasn't been loaded previously. This effect where Fg is less than OD dash and OD is called Bauschinger's effect. We next look at Hooke's law. Hooke's law is quite important in mechanics of materials and used in many chapters. We take the earlier discussed case where a rod was suspended from a ceiling and it was subjected to a load P. The rod extended by a length del L. Experimentally, it was found that del L is proportional to the length L to the load P and inversely proportional to the cross-sectional area. So del L is proportional to PL divided by A, which we can write as del L by L proportional to P by A, or strain being proportional to stress. Due to the fact that strain is proportional to stress, when we plot a stress-strain curve, we get a linear line. The slope of this line is denoted as E. It is called the modulus of elasticity or Young's modulus. Since this line passes through the origin, the equation for it is y is equal to mx. Here m is E, y is the stress, and x is the strain. So we get stress is equal to E into strain, which is written here. Sigma is E into epsilon. The value of the Young's modulus is 200 GPa for steel and 75 GPa for aluminium. It is a material property and varies from material to material. For an isotropic material, it is a constant, but if the material was anisotropic, then it will vary in different directions. A fair bit of what has been mentioned here was discussed earlier. Hooke's law is applicable only when the loads are low and the stress-strain curve is within the linear region. The behavior of the material in this stage is elastic. Here we consider deformation under axial loading. If we have a bar subjected to axial loading, then the deformation it undergoes would be extension of the bar or reduction in its length. Find extension or reduction use is made of Young's modulus. Consider a material made of steel. Young's modulus has been found from the experimentation of steel bars with stress-strain curves drawn. Thus, we have found the behavior from other steel bars and can use the knowledge to a steel bar for which we have a problem. The problem here is the extension or reduction of the length of the bar, knowing the stress acting on it and its length. Earlier, Hooke's law was given as sigma is equal to E into epsilon. So Hooke's law can be written in this form. Now, if delta is the extension or reduction in the length of the rod, then epsilon is equal to delta divided by L, and sigma is equal to P divided by A. So we can write delta is equal to PL by EA. This formula is applicable as long as P, E, and A is constant. For a rod, if different portions have different P, E, and A, then we have to consider the portions where they are constant and find out delta for each of these portions, and then finally sum delta up for the whole rod. So if there are n portions, then delta is summation Ei Li divided by Ei Ai. I is equal to 1 from 1 to n. Consider the problem here. The whole length could be divided into 3 portions for which E, E, and A are constant. These 3 portions are shown as L1, L2, and L3. So we can get extension or reduction for these 3 cases and then sum them up to get the extension or reduction for the bar as a whole. Now consider the portion L1. Let us take a section as shown. Then on this section, considering from the right, P1 is the only force acting. The area is A1 and the modulus of elasticity is E1, which is represented here. Now consider the second portion. Let us take a section here. These two forces act in such a way so that the resultant P2 acts through the centroid. Then if we take a section here, then considering from the right, the force acting will be P1 minus P2. The area is A2 and the modulus of elasticity is still E1, which is represented here. Consider a third section here. Again, the resultant of these two forces is P3 acting through the centroid. Then the force acting on this cross section be P1 plus P3 minus P2. The area is A3 and the modulus of elasticity is P2, which is represented here. So using this expression, we can get the total delta. Consider now a different case. The bar is subjected to a load P. The material is constant and the modulus of elasticity is given as E. But the area varies throughout the length of the bar. Then delta can be given by this expression. There can be an analytical solution or a numerical solution. If Bx divided by Ax is integrable, then we can get an analytical solution. However, if it is not integrable, then the problem has to be solved numerically. Here in this problem, we have a beam ABD. A force P is applied at A, and the beam is held by two bars, BC and DE. Now we see that for the bars, E and A are given. We know the length of the bars. So if we can find the force of the bars, then we can find their extension. Now ABD, the beam is straight, and after deflection it will also remain straight. Now consider that BC has extended to a point somewhere here and DE has extended to a point somewhere here. Then knowing the new positions of P and D, we should be able to find the position to which A has moved. In this problem, the maximum deflection is given and the force applied is not given, and we are asked to find the force. So the problem is in reverse, but we'll solve the problem in a straight manner. We'll think that we know the force and we'll find the maximum deflection. So to start with, we find the force in BC and DE. If we take moment about D of the bar APD, then we can find the force FBC. If we take moment about B, then we can find the force FDE. Now knowing the force in BC and DE, all other values being given, we can find del BC and del DE. So the extension of the bars. Now after the force has been applied, this should be the new position of the bar ABD. So del BC we have found and del DE we have found. Now for convenience purposes, let us consider the triangle A dash, D dash, A double dash. Then B dash, B double dash is del BC plus del D. So we have found that here. So I have found B dash, B double dash. We know B dash, D dash this length. So we can find tan theta. Now tan theta is also given by A dash, A double dash divided by A dash, D dash. So this distance. Now we know A dash, D double dash this distance. So we can find A dash, A double dash or del AD. Now if we subtract del DE from del AD, then we come with del A. We find del A, which we have already know to be 0.4 millimeter. So we find del A in terms of P. So equating that, we get the value of P. Like the last problem, this is a problem where we have used the formula delta is equal to PL by EA and some geometry. Now for AC and BE, we know the length and we are also given E and A. So given the force, we can find out the extension of AC and BE. The force in D is given and we are required to find out the deflection at B. Now since D is more towards AC than BE, we understand that AC will deflect more than BE. CD is a straight line and after deflection will remain a straight line. So we can find the point to which E has deflected and we can find the point to which C has deflected, and from there using geometry we should be able to find the deflection at point of B. Even though the force here has been given, we have proceeded as in the previous problem by considering the force initially as P. So in terms of P, we can find out the force in RA by taking moments about E and RC by taking moments about E, and we can find out the force in E by taking moments about C. So we have done that and we have found delta CA here and delta PE or EB. With these two deltas found, we have to use geometry to find the deflection of D. So this portion, we have drawn this line for construction purposes to help with our calculation. So this portion is del CA minus del EB. Since we can find this portion, we also know CE. We can find tan theta. Then using tan theta, since we know DE, we can find this distance or del D minus del EB. We know del EB, so we can find del D. So here we have found out first del D in terms of P, load P, and then put the load in to find out the value of del D.